Okay, so now what we're going to do is we are going to look at spectrometry, and we're not going to go as much into the deeper workings, mainly because there isn't as much to go into, and also because it's in terms of the concept, it's slightly easier to sort of wrap your head around it, I think. I suppose it doesn't have as much to think about as compared to, say, NMR spectroscopy, especially high resolution proton NMR. So pretty much what happens is that the sample is placed, so like this is what like the machine will generally look like. And what will happen is that the sample comes in here, you bombard it with electrons, and essentially it breaks up into its component ions because you've just bombarded it with electrons. So what will happen is that it will take like the electrons, it might lose electrons, and it will basically just be separated into its fragment ions. So that's like the general idea there. So if it doesn't make sense, we can obviously we can go through it a little bit more, but that's just like that general idea that I'd like you to understand. Now, this is what we'll mainly be dealing with. So before in the last slide, that was a machine on what the machine looks like, but this is the spectra that we'll see that's useful to us. So there are a few things that I really want to point out here, and the first of these is the base peak. So the base peak essentially is the one that is the most abundant. So the fragment ion that's the most it has the highest relative intensity, or it's the most abundant, pretty much like the one that's produced the most. I guess you could say, and I'd also like to point out that this is the original molecule. Okay, so it's CH3, CH2, 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 CH3. We bombarded it with electrons, and so it would have lost an electron then, and it would have become positively charged. Okay, so then it's just lost one electron. It hasn't lost any of its like fragment ions or any of its like atoms. So then we would just call this the molecular ion peak, and it's the one that has the highest mass to charge ratio. And so the mass is just like it's basically molar mass, and the charge is just like the charge of the compound. And here it'll always the charge of the compound will always be 1. So what the mass to charge ratio basically tells you is the molar mass of that particular fragment ion. So this is the molecular ion peak. So that's the original molecule. And so then basically this is just telling us the molar mass of the compound. And as you can see here, from this fragment ion, molecular ion to this fragment ion, we've lost these CH2, CH3 group. So we've lost those. And then that's why we've also got a lower mass to charge ratio, because we've lost that CH2, CH3 group. And so we've basically just lost like the molar mass from the from the fragment from here to here has decreased, and that reflects on the mass spectrum. Now, we can also have different isotopes. So for example, we have isotopes of chlorine. So we have chlorine 35 and chlorine 37, and basically these have the same number of protons as each other. So they're the same element. It's just that they have different numbers of neutrons. And what happens with these neutrons is that they can contribute to slightly higher or slightly lower fragment ions. So for example, at the mass to charge ratio of 88, we've got, there would have been 2 chlorine 37s, sorry, not 36, 37s. And at a mass to charge ratio of 86, it would have been because we've got 1 chlorine 35 and 1 chlorine 37. And that basically is just because of isotopes. So you mainly need to worry about isotopes when you were talking about haloalkanes. You won't really need to worry about other sorts of isotopes. Those are the main isotopes that we'll worry about. Now we're going to get into a few practice questions. So how can we determine the identity of this straight chain alkane? And so what I want you to think about is what information can you get from this? So if you just go back to here, okay, this is the 2 main important pieces of information that we can get from the mass spectrum. So I want you to think about the question in terms of what information can I get from the mass spectrum, basically. Okay, so for part A, the molar mass of the compound, well, that's just given by the molecular ion peak. And so we can see here that it's at about 114. So that's part A. And for part B, we want to find the mass to charge ratio of the base peak. And if we just read off the mass spectra, it's at about 43. It's at the mass to charge ratio of the base peak, the one that's the most abundant, which is this one over here. It has a mass to charge ratio of about 43. And for the last part, question C, the name of the compound. So we know that it's a straight chain alkane. So if we look at the molar masses of the straight chain alkanes, well, the first one is methane. Can it be methane? Well, the molar mass of methane is 16, so no, because we want the molar mass, obviously, as we found in part A, we want it to be 114. And so what we can do is, well, let's take a look. Maybe could it be pentane or hexane or heptane? And eventually what you'll find is, and I'd encourage you to do this, is that if you determine the molar masses of all the possibilities, it's only octane that matches the molar mass of this compound most closely, because the molar mass of octane is 114, and that matches exactly to the molar mass of this compound, which we can tell from the molecular ion peak at 114 at a mass to charge ratio of 114. Okay, so let's take a look at this one as well. So essentially here, we want you to, what I'd like you to do is to determine what, so I've told you this is a ketone and that this is an amide. And what I'd like you to determine is how many carbons are in each of these two. Okay, so essentially what we want to do here is we want to determine what kind of a ketone would this be, knowing that the molar mass is 72 and knowing that, for that amide, the molar mass is 59. So what we'll do is we know that it's going to be something like this. So it'll have C and then double bonded to O. And then next to it, it must have some sort of like a CH2 group. Okay. And now what we'll do is we'll see that, so it has to have that C double bond O. So it has that, this has a molar mass of 12 and oxygen has a molar mass of 16. Okay, so then that's 28. So what we'll do then is we'll do 72 minus 28, which equals 44. So we know that the rest of the carbon chain, okay, or the rest of the hydrocarbons here, they must be equal to, they must have a molar mass of 44 because that's what's left over. So then we know that this CH2 group that has 12 plus 2, which is, so 12 is the molar mass of the carbon. The molar mass of the hydrogen is just 1. So that's 12 plus 2, which is equal to 14. And then if we add 14 to this, okay, we'll go 58. Well, that's not quite enough. So then what we need to do is, it means that we need to add just one more. Okay, so that's what we'll do now. So if you just add one more, then you should get 72. Right, sorry, so, okay, sorry, so allow me to just backtrack for just 1 second. So we've got this CH group that's contributes to 12 plus 16, which is 28. Okay, so then we went 72 minus 28, which has 14, 44. So that's 44 is left. Okay, so sorry. Okay, sorry. Just 1 second, please. So we've got that CO group, okay, and that contributes 28. Okay, so 28, and then we have, let's say we have one CH2 group on that side, so that's plus 14. Again, this isn't quite 72, so we still need to add more. So then that's CH2 on this side as well. And then that's 14, but that still isn't enough. So, and how short are we? So we go 28 plus 14 plus 14 is equal to 56. Or in other words, how short are we from our end goal? We're actually just, sorry, so we're actually just 16 away. And so, what we would need to do, so now what we would need to do is just finally add the remaining group. Okay, so that we'll just add that at the end there. And so we should end up, and sorry, so that, so that's 15, right? But we just need one more, so we'll have to add that there. So that's CH3. And the reason for that is because we can't end on CH2. We can't end on this. We have to end with CH3. So that's why we have to add another hydrogen there. So essentially, that was a little bit messy, but essentially what you want to do is you want to think about, okay, how many more groups do I need until I get to my goal? And that's essentially how you want to approach this. And so we'll approach the amide in a similar fashion. So here our molar mass is 59, and we know that the amide is made up of that C, like that CONH. So CON. Okay, so then that contributes 12, that contributes 16, and that contributes 14. So these are just the molar masses. And so we, in total, that these contribute a total of 42 grams per mole to the molar mass. So we know the molar mass is 59 in total, and that means that we are just 17 off. So what we would do is with 17 off, so we can only add one more carbon because a carbon is 12. And then if we add two more, and add another carbon after that, okay, so we've got, let's say we add one carbon, okay, so now we're like this, drawing the group, and we're in like this. So now we've got 12 plus already, so that's 42 plus 12 again, that's 54. If I add another carbon, then I go beyond 59. That's too many carbons. So now I know that I only just need to add hydrogens. So I'll just add them in here. So now I know that my molar mass must be, also my molecular formula, sorry, must be C2H5NO, like that. And then you can check if the molar mass is matches or not. It should. And so that's how you know that you've got the correct answer.